Okay, so any other questions from 11.8 or even 12.1? So we have 11.7 and 11.9 is now extra credit. Right? 11.9, the ideas in 11.9 are not used very often, so yeah.
Are you going to show us how to graph?
Yeah, today we're going to talk about how to graph surfaces.
Like that one.
So you've already started 12.1 homework. Okay. So we're going to talk today about, and in fact, they give you an approach in the book, and we're basically going to do the same thing. And it's sort of like what I was saying earlier. I don't know if you guys remember, I was asking if there's anybody who does a lot of art. And very often, in some types of art, you'll set up some chicken wire in a certain form, and you'll cover it over with who knows what, plaster Paris or sheets of something. Right? It gives a nice form. I'm thinking about creating like a float or braid or something. But that's the idea. We're going to lay down the chicken wire, the structure, by figuring out what it looks like in these different planes, and then try to connect those. And it's not going to come out pretty in every case. It's not going to look as nice as the book because they used a computer to do it, so it's a little bit easier. So yeah, today we'll talk about the steps to put together a 3D graph of the surface. And on the way there, we'll talk about the domain. What does it look like? What does a function mean now that we're talking about 3D? Does it mean the same thing as it did before? Those kind of side issues. Any other questions from homework? Okay. So what we did last time in section 12.1. Equations, yeah. We did, what was the basic equation of a plane yet?
A prime times x minus x naught.
Equals 0. And then of course if you bring the a's in and you get ax plus by plus cz equals d, where d is the appropriate thing. D would be ax naught plus by naught plus cz naught. You just pull that over, it's all constants. Cool, and that's nice. That is really nice. And it's not necessarily what we would expect for this, right? But that is a plane that defines all the points that lie on the plane. Yes, sir?
What is D?
A D again would be the ax naught plus by naught plus cz naught, because you're going to add it to the other side.
Right.
Cool. So it's just collecting all those constants.
How does that affect how it's graphed, the function or its appearance?
Doesn't.
Doesn't.
Yeah. Just putting it in a certain format, it's still the same plane, right? When you go to graph this, you would still, if you wanted to graph, if I gave you an equation of a plane and I asked you to graph it, you would just get a few points, and then you could try to graph that plane, right? Or I would actually find a few points, get some vectors, and that would make it easier to kind of graph the plane, right? Because another way, there's several ways to define a plane, and one of the most basic ways, and let me not spend too much time on this, but it's a good view of this. A line is start at some, let me just make this more general, start at some point and then plus some t vector v, right? That's a line. So there's only one true variable in it, one parameter. Another way to define a plane besides what we just did there, and you got to be a little careful if you want to define it this alternate way. How many variables should I need for a plane? How many parameters?
3.
Careful. When I say variables, I really, really mean independent variables. There are only 2 independent variables up here. The third one would be dependent on those then. Which one is which? I'll pick. I don't care, right? Whichever ones I throw stuff in for, the last one is dependent. You guys with me? In algebra, y is always the dependent one, basically, and x is the independent one. But we know now that's not the way it has to be. And in fact, very often in this class, we get really hung up on X and Y being the input and Z being my output. That doesn't have to be that way either. It doesn't really matter. The orientation of my coordinate system really shouldn't determine anything. I could have something, I always call this like a Pac-Man ghost sitting this way, or I can have him sitting this way. So here he's kind of like around the Z-axis. Here he's around the Y-axis in this case, or I can have him centered around the X-axis. So it doesn't matter which variable is considered independent, dependent. But I do have one true parameter for a line. That makes sense. That's the definition of linear, right? And what about a plane then? So that's one-dimensional thing. And then for a plane, I'm going to have, actually, this is kind of where it gets kind of cool. I'm going to have like S plus T. As long as what? What's definitely got to be true here? What do you think's got to be true about the U vector and the V vector?
As long as they're non-zero.
They're not multiples of each other. They're truly, they have some kind of angle between them that's not 0 or 1/8. So an example of this is the xy plane. My two vectors are the I vector and the j vector. Don't I capture the entire plane if I take all multiples of I and j and all combinations of those multiples? Isn't that the definition of the xy plane? You guys kind of with me?
Mm-hmm.
But this, so there are alternate ways to get to what a plane is. Right? So this other method might come in handy at some point. Okay. So it should make sense. In order to get a line, I need 2 points. In order to get a plane, I need 2 vectors. And in both cases, they must be unique. If I give you the same point twice, that ain't going to give you a line. Right? Not a single line, anyway. Okay. So that's sort of like what we did last time. We got here. I don't think we got too much further than that.
Oh, for the definition of the plane, do you also need to have like a defined starting point for it, or?
An origin?
It has to have, this one kind of inherently implies that it has to have
On the 2 vector.
yeah, on the 2 vector one, you're right. It has to have
You'd also
this would give you a plane that might be parallel to the one you really want.
Yeah.
So then you throw in the point that you want it to cut. Yeah, good. Because these vectors would be in standard position, so you'd always get that, what I would call a standard plane. And then you bring in a point to move it to where you want it to be moved to. So this method is another method to get there, but it's not even complete. I'm not going to spend a lot of time on this because I don't really do it that way too much. Okay. I don't think we talked directly yet about, oh, that's where we left off. On the test, I had an extra credit problem about how do you tell if 2 planes are parallel, I think it was. A few people got the idea, a few people I could tell knew the answer already, which is fine. I mean, that's the way it goes. But some people actually kind of worked it out. They didn't even know what the words were for what they were describing mathematically, but it was perfect. It was exactly the answer, which is basically, if I have a plane, it kind of is defined and it automatically defines a normal vector. Right? And in fact, the normal vector could be either that way or that way. We'll just kind of, for the sake of argument, we'll just say it's that way. I feel like the other way, just turn around. So for it, yeah.
I was gonna say, so for any cross product of any 2 vectors in that plane, the normal vector would be equivalent to any other plane?
Exactly. Cool. Right? Because
Parallel.
if I have a plane that's 2x minus y plus 4z equals 7, what's the normal vector?
2, 1, 4.
But what about the plane 4x minus 2y plus 8z equals 14? What's the normal vector? Right? Now, of course, this is a multiple of this because this is a multiple of that. You guys with me? So these are really the same plane. So normal vectors, the way they point is not, you don't have to define that to get the plane. In fact, if you cross 2 vectors, if you choose to have these 2 vectors here, and you cross them, U cross V, you get that. V cross U, you get the other way.
So as long as they're parallel.
As long as it's on that line that it kind of sets up, right?
So those two normal vectors, as long as they're parallel or anti-parallel, then you're fine.
They're not, yeah. So your normal vector could either be pointing up from the plane or down. It's the same idea.
As long as they never intersect. As long as they're two normal.
So now let me bring the second plane in here. So if I want to show that these two planes truly are parallel, then obviously all I have to do is show that the normal vectors are parallel, right? So you would hope, now watch this. If I have, this is this plane, right here, 2x minus y plus 4z, that's this plane. And this plane is 2x minus y plus 4z equals 3. It's exactly the same case as in good old algebra when I had y equals x plus 4 versus y equals x plus 3. Of course these two are parallel, right? Because the only thing I changed is its intercept. So the same thing here, really. The only thing I changed is the intercepts in a way also, but I just changed what point I want the plane to go through. So I just moved it over, up and down. You with me? So this should, from just looking at the equation, these should be parallel, because it's analogous, there's the correct grammatical use. It's analogous to this situation back in algebra, right? Now how does that match up with what I just said to show that two planes are parallel? Well, this normal vector is 2, negative 1, 4, and this normal vector is 2, negative 1, 4. So they're obviously parallel. Those are multiples of each other. One is 1 times the other one, so it's beautiful. You guys with me? These two here technically aren't truly parallel because one lies on top of the other one, but we would still call them parallel. Yeah.
If the d for those two different equations, if those d are not the same scalar multiples as the other variables, then would the plane still be parallel?
Definitely. Because right now, are these the same scalar multiple? This is a scalar multiple of 1,
Right.
whereas this is a scalar multiple of 3/7.
Right.
Right?
Okay.
Who cares?
I'm saying, yeah, with the 14, like, what if it was equal to 15? It wouldn't matter.
Beautiful.
It wouldn't matter?
Exactly.
Still
They'd
good.
still have, this normal vector for this would still be this,
Okay.
which is still a multiple of this, so those normal vectors are parallel. Therefore, the planes must be parallel. Cool. To show that the two planes are perpendicular, what would you show? Dot product of the normal vector would equal 0. Beautiful. Right? So is that normal vector? A lot of you guys sort of have the idea, but you can't dot product a plane with another plane. That doesn't make any sense. Right? So you have to define, there has to be some defining vector, and there is. The normal vector is the defining vector for a plane. So it steps in and shows all these relationships. You use it to show it's parallel. You use it to show that they're perpendicular. Because we know how to deal with vectors. Right? Okay. So, going along with the idea of, I really like to teach these things trying to build on what we know from algebra already. Because like I said the first day, I think, a lot of the ideas in here are really simple if we just accept they're an extension of what we already know. There are a few things that aren't the same, obviously, but a lot of things aren't. So, for example, if I have, the way I try to teach this sometimes in algebra, if I tell a student, can you graph this on a number line? Then hopefully they can. But then, one way you can explain the special case of x equals 3 in 2 dimensions is to say, and this is the special case y equals 0, yeah. So if I put my y-axis here, thankfully in the right place, this is one position. Now what about if y equals 1? X still has to be 3, and so forth, and that's how you pick up this guy, right? So that kind of comes off, I think I already said something about this. What variable is missing from this equation?
Y.
And what do I end up being parallel to?
Y.
The y-axis. Interesting. And of course I have to be. If I wasn't parallel, I'd have to hit it. If I hit it, there must be an intercept. And how can be an intercept if the letter didn't show up? right? To find the y-intercept of x to 0, 0 equals 3, okay, not good, right? So of course it's got to be parallel. So, for example, even before we get into anything else, that plane has got to be parallel to what axis? Z. So it can't possibly hit the z-axis, right? Cool. And in fact, we can take this actually, I didn't plan on this, but this is kind of a cool way to do this. The line x plus y equals 3. So of course, y-intercept is 3, slope is -1, so there's the y equals 3. X plus y equals 3. Let's pretend like that's the right scale. There you go. That's perfect. Now extend this idea to the next dimension. Just go one more step up. It's the same step you take. Here's one dimension, and students coming to MAC 90, they love that one dimension. They're normally pretty good at it. Little closed circle, and shade, all kind of stuff. And then you try to throw a second dimension at them, and it takes them a little while to get used to that. So we're having the same transition, really. We're going from the dimension we're used to one more dimension on top of it. What would this graph look like then in 3 dimensions? This is for z equal to 0. So what about z equal to 1? It'd be the same line, wouldn't it? Z, because z doesn't affect this. It's what it is. Z equal to 2. So what would this really do? It would, of course, be this plane. Cool? And notice what it does. Does it ever intersect the z-axis?
No.
Hell no. Of course not. Yes, sir.
What about x plus y equals 0, where it would pass to the origin?
So if I have x plus y equals 0, so that would be here, and then it would go like that. Cool. And that's the extreme case where, of course, z equals 0 works there, right? So it would hit z everywhere. In general, if the letter's missing, it can't hit it. Or in the extreme case, in the one case, it hits that thing everywhere. Cool. Okay.
The z is not really 0. The intersect with z is 0.
Well, in what I've drawn here, this is z equals 0.
No, on that one. The first one you were talking about. Yeah.
Here?
Mm-hmm.
Yeah, this is the case where z equals 0. I've drawn the plane where z equals 0. Z equals 1, it'd be the same line again.
Yeah.
Z equals 2, 3, yeah. So this is the plane that represents z equals 0. Cool.
Okay.
So in a way, I know what you're saying. This is the intersection with the xy plane.
Mm-hmm.
Intersection with the z equals 0 plane.
With z equals 0.
Beautiful. Okay, cool. So we're saying the same thing. I like that.
Yeah.
Okay. How are we doing so far? Does everybody get a feel for this? I mean, I like this idea. This is a way to step into these surfaces in 3D, is to see what connections they have with what we already know.
Are you defining x plus y equals 3 as just a line in the xy plane?
That's how I started. Just like here, I started with just a one-dimensional number line.
But yeah, I was listening to what you guys were talking about right here. So you're now saying it's a plane going a vertical?
Yeah, so if I were to, here's the z-axis now.
Right.
So if I want to draw this in 3 dimensions,
Yeah.
somebody has to tell me to draw it in 3D, because if they just said graph this, I would graph this. Just like if I were a student and they asked me to graph that, I would graph that. I'd have to say
Yeah.
on a Cartesian coordinate system, right?
Yeah.
Otherwise, I can't really complain that they're wrong. They're technically right. But I got to tell them it's actually in 2D. So here, this is in, graph this in 3D. All you have to do is say, this is for z equals 0. For z equal to, I don't care, it's going to look like this same thing.
Yeah. It's never.
So then it's just going to extend this line out. And that is the official definition of a cylinder in 3D. We think of a cylinder, of course, and you can see how the extension is made. A cylinder is a circle that extends from there, right? So I'm really doing the same thing. So a cylinder in this class, in multivariable calculus, in math, really, is anything where you take a curve and then you take all the lines that intersect the curve and are parallel to some other given line. So what I'm saying is like the z-axis is my line. So parallel to that would be this sheet coming off, right? That plane. Are we good with that? Cool. Maybe. All right. Yeah.
But you said cylinder, would that have to be a circle like X squared?
No,
plus
no,
Y
no, no.
squared?
So it's more general idea. What we think of as a cylinder, it's sort of like, does anybody know what the name prism means? And don't tell me about bending of light. The shape.
the triangle, which is
Could be a triangle. It's any repeated shape. Any repeated shape is a prism. So this is a more general definition of cylinder. Cylinder for us is a circle that's been repeated. And it could even be non-right cylinder. So it could be some cylinder like a silo that's had a bad gear, right? So it could be like that. And that would just be me taking some other, I could even have it going this way, right? So a cylinder is just defined, and here's the definition. The definition gets a little bit disgusting. It's on page 778. Given a curve C and a plane P. So I've got a very specific situation up here. My curve is a straight line. And mathematically, we should have no problem with saying a straight curve. We can say that with a straight face. Just like we can say a straight angle with a straight face. Given a curve C, this is my curve C, and a plane P. And what's my plane P? XY plane. So my plane P is the XY plane. Given a curve C in a plane P and a line L not in P. So I can't pick this line. So the line I picked was the z-axis, for example. Or something like here. Going through this point here. This line here. You guys with me? A cylinder consists of all lines parallel to that line L that pass through C. So if I do use the z-axis, this cylinder would be the line that passes through C that's parallel to that line that I'm using. How are we doing so far? Is that cool? So if my line, if instead I wanted to use this line, then everything would come out like this. It'd be a sheet of paper coming out like that instead of straight up and down. You guys with me? And of course that could happen depending on what the equation looks like. Right, we're sort of working our way through the general idea of what it could look like, and then we're going to get to the specific, what does this equation end up looking like? What does this equation end up looking like? Yeah.
But in the instance where you just tilted your paper, then there would have to be a z variable in the equation. Because
Exactly. My equation would be different then. This equation specifically would be the z-axis is my other line, and then it's parallel to that. I like it. So if I put a z in there, that would make it tilt somewhere else. Yeah, cool. Okay, how are we doing so far? We doing okay? Basically. So I could have, for example, I could have this be my curve, C. And then I could still choose the z-axis as my line. So what would this look like if I did a cylinder out of it in 3 dimensions? It would just be the same shape repeated forever, right? So it'd be the same shape, a sheet, and you can almost see it like some road that's gone through a lot of weirdness. Or some road that's really fun to drive down out in the desert somewhere, right? But it's a road, so it goes on this way for a little while.
It'll be like a sine wave.
Sine wave, exactly, but not just 2-dimensional, I'm talking 3D, right? So you can tell that this is a very simple example of a possible 3D surface because one of the dimensions is purely follow what the 2 dimensions told me to do, right? In general, this 3rd dimension can do whatever the hell it wants to, really. We're not quite there yet. We're getting there. Okay. So this is sort of like learning lines in algebra before you learn parabolas stuff. So this is really a line in 3D is now we're sort of equivalent to learning that in algebra. We're learning just straight from here first, and then we're going to learn how the hell to make it do whatever it wants to. Oh, good. So here's a really useful tool that the trace of something. And this is actually, I think you were making this point earlier. A trace is really just a cross section of something. It's more specifically though, it's got to be a cross section through a plane that's parallel to one of the coordinate planes. And is everybody cool at this point when I say coordinate plane? Give me an example of a coordinate plane. The XY plane. So I could use a plane that's parallel to the XY plane. So let me do this. Let me actually, I should have done this earlier, but I didn't quite get here in time. This is obviously easiest to see when you have a computer-generated image over a Jeff-generated image. So with that statement, I'm hoping you understand that I will be pretty lenient on your 3D sketches, right? To a point, within reason. They're not going to necessarily be pretty. Some of them will be. And, you know, I'll be jealous of that ability, but it's all right. Cool. So, real quickly, algebraically, while this thing is warming up, algebraically, here's what a trace really does. If I have the graph, if I have y plus z equals x squared minus 1. The yz trace, what's got to be true to capture the yz trace? X equal to 0. And of course, so what's the equation of the yz trace? Careful. Equals -1, and then you can, whatever you want it. Normally we use z as the independent when you do that. It's because you're going to draw y and z. So then you can draw your trace. So before you try to go directly to a 3D sketch of a surface, you do the cross sections on, at the very least, the coordinate planes themselves. I could do a cross section with not x equal to 0, but x equal to 2, which would pull it out on the x-axis just 2. And then I can graph that also, and then just connect those two. Right, so if I've got a picture that's one of those ghost dealies, right? Oh yeah, ghost dealie. The trace in the xy axis, you can do this, Joe. There you go. The trace in the xy axis for one of these ghost dealies, do I still have it up here? No. So what I'm talking about is, of course, what do you think the name of this thing might be?
Half
I thought you said Pac-Man. I thought you said Pac-Man.
Yeah, it's like a ghost Pac-Man deal. What do you think the technical name might be? I don't think that might be the technical name. What's the basic shape of this thing? Yeah, it's a parabola. So this is what's called a paraboloid. Right? So any Metroid fans, it doesn't quite correlate, but that's all right. So in the xy axis, the trace of this would be a circle. And in fact, the trace to anything parallel to the xy axis, what do you think it is? Circle. So I could do the, this is x final. I could do, this is for z equal to 0. What about for z equal to 2? It's going to be a smaller circle. And maybe it goes up to z equal to 4. It's just going to be a point. Do you guys get that now? This is my chicken wire. This is part of my chicken wire. This is my xy trace. And these are traces in planes parallel to the xy plane. How are we doing so far? So this is the trace for z equal to 2. This is actually the trace for z equal to 4. And of course it could just be a point, because above z equal to 4, what is it? Not a damn thing. Okay. And then what do you think your traces are going to look like in like the yz plane or the xz plane? They're going to be parabola. So here would be, that's fantastic. And then over here you got similar idea, right? Oh, I should really connect with my circle. That would probably be a good idea. All right. Now, considering that this is really disgusting and it's done by me, very little artistic ability. Since you kind of followed me doing that, can't you see that that parabola there is tilted that way? It's on the x-axis there. You guys with me? And you can see this one. That's what I call, that's my chicken wire. That's basically, you could stop there. Don't try to shade it in unless you are artistic and you want to show off. You guys kind of with me? And that's not even on isometric paper. I mean, it's going to be a lot easier on isometric paper, obviously. But these traces are what help us, dear God, with graphing 3D surfaces. Let me try to show you a couple.
So on the test, we won't be asked to fill in a plane, we'll only be providing the chicken wire?
Do it one more time.
On the test, we'll only be providing the chicken wire, we won't be shading in? at all?
Exactly. And in fact, normally what I do is I even have you, what I did last semester, what I'll do again this semester, is I give you a completed surface, and then you guys on top of that fill in the chicken wire, using algebraically what the function is.
Nice.
You with me?
Because whenever I try to shade in, it just like, looks like one solid blob of color.
Exactly. And it's not easy. Then you've lost. This is a lot easier to tell
You
what's
lose
going
all
on.
the information you used to have with the chicken wire.
Exactly. I like that my phrase chicken wire is at least catching on with a few people.
I don't want KFC.
I'm from Ramona, it's a hick town.
Let me see. The most simple example of a paraboloid. Actually, let me ask you.
Excuse me.
Yeah.
In this case, if we choose another trace, it will be difficult, right, to control?
Yes,
Because we will
thank
not
you.
have a,
Obviously, trying to get a trace. For example, you're thinking along like maybe this plane, right? Because I'm doing a trace along this plane and along this plane. But to get a trace along this, you know it's going to be parabola in this simple example. It actually would be useful for a more complicated surface to be able to do that, but the algebra behind that, like you figured out, would itself be freaking complicated. So that's why I don't know if you guys are with this, but it's very simple to get the YZ trace, XZ trace. You just make one variable 0, right? But to get some arbitrary at an angle from something plane, the trace there, not going to be very easy. Here I know it's just going to be a parabola like that, right? I missed my edge of the circle there, but it's too bad for me. It'd be a little OCD. There you go, Jeff. That is beautiful. I don't know if you quite understand the question. We stick with the coordinate planes and parallel to those because it's easy to figure out what to set the variables to make that happen. If you wanted to do a plane that was at a 45-degree angle to something else, not the most straightforward math in itself. So it's easier just to stick with what's easy. So put the chicken wire down, right? Okay. This guy's good.
Professor?
Yeah.
I'm just looking at your drawing. Seeing how it's x squared minus 1 for z equals 0, wouldn't it not be standard graphing normal?
Where are we at?
For z equals 0.
Oh, I didn't really graph this.
Okay.
This is just a general example, something
Okay.
easy to point something to. I didn't really graph that.
Okay.
To graph this though,
It'd just be off
you would first graph this line, right? Here would be your y. Oh yeah. Here would be your YZ plane. That's the YZ trace. So you would graph the line z equal negative y minus 1. Right? So you have the negative 1, and then it's negative from there. So it's basically, yay. Okay, so there's the YZ trace. What would the, I got kind of sidetracked after that, but what would the XZ trace, what would that be?
Z is equal to x squared minus 1.
Which is nice, it's just a parabola that's been shifted down by 1.
Right.
With me? Because of course to get the XZ trace, you make y equal to 0. Cool. So then you can graph in the XZ plane. You would graph this. And that would be, now, in the end game would be to put all of these traces together in 3 dimensions. You with me? Right? That would be the end game. But you first do it in those three basic coordinate axes traces. You do those first, and then you try to stick them together here. This one was pretty simple, parabolas and circles. Yes. Right, this one's not too bad either. I mean, this in the XZ, it's just going to be a parabola shifted down by 1. So it's going to do this. And in the, what's left? XY, yeah. In the XY, it's going to be same thing, right? You with me? A little bit? So now I am kind of curious how this thing looks up at the end. See if I want to try this. Almost. Let's see. So in the YZ plane, let's first do these. In the XZ plane, it's this parabola. So in the XZ plane, it's just going to be, the trace there is going to be this. Don't get mixed up with that. Yeah, okay. So it's going to be this. Oh, I keep trying to fill that in, but I don't have to do that. Basically that there in the XZ plane. You with me? In the YZ plane, it's going to be a line. And in the XY plane, it's really the same thing as this. XY trace is going to be yeah, y equals x squared minus 1. Thank you. So that trace is going to be like this. No, Jeff.
No.
So there's some chicken wire.
No.
That's a Z.
Oh, what did I just? Oh, yeah, yeah. Thank you, thank you, thank you. I was thinking to myself earlier to be careful about that. Okay. Yeah, what I want is the XY trace. Thank you, thank you. So that would be here. Oh. Down there. So negative, and then from there, like this. Of course, I had to come up with an example. It's kind of really disgusting.
Pencil.
Yeah. Now this would be an excellent candidate. This is a really easy one to do. This would be a really good one for doing more than just the coordinate planes. Do, for example, what would it look like, and because it's really not easy to see with just doing that, how this line idea really fits in. But think about what happens, not for, let's see, y equal to 0, but what about y equal to 2? So coming out here, y equal to 2. On that plane here, y equal to 2, what would happen? Z would equal what?
X squared minus 3.
Okay, so in the y equals 2, it dips lower down, doesn't it? And do you see now how that line comes into play, this line here? Let me see if I can go with this. I need more colors, and I didn't bring many with me today. Where'd that green one go? I had. Shoot.
In your bag?
Oh, there it is. Okay. I really want you guys to see this here. So let me stop right there. Are you guys semi-cool with what we've done so far? What we've done so far is nothing much, right? We put one parabola, the XY parabola, that looks like this. We stuck it on the XY plane. There it is, right? So if you were standing up here looking down, it would be our nice, normal XY parabola been shifted down by 1.
And this is all going back to various graphs of y plus z is equal to x squared minus 1?
Various cross sections of that. You with me? Everything we've done so far is a cross section of the end result. So to build this guy up, we start with the cross sections and hope they kind of come together. They did here. All I needed here really, to tell you honestly, I did do a few other than just the coordinate axes. I did like this one for z equal to 2. So we're going to do a very similar thing here. Y equal to 2 instead of just y equal to 0. So now I am parallel to the XZ plane. So I'm doing a trace in the y equals 2 plane, which is parallel to the XZ plane. You guys kind of with me? So I'm going to graph that here. And you can see how this would be a good one for isometric paper. This is where it gets a little bit vague if you don't have nice isometric paper. Yeah.
I don't mean to digress. You said at the beginning of class that you were talking about independent variables and dependent variables, and it looks like you're rewriting each equation z equals. So I'm curious, just
That's me. That's really just me. I'm used to putting when I don't have all three variables. Obviously x and y, we put y as the vertical axis,
right.
and then in other cases I always just put z as a vertical axis,
Okay.
because that goes along with z being normally the one that goes up and down in 3 dimensions.
Okay.
Do you have to do that? Hell no.
Okay.
You even have to have one. You can have them like that if you want. I don't care.
Right.
But that's how I personally normally set it up. But it's a good point. You don't have to do it that way.
Yeah, because you were talking about ax plus by cz equals d.
But to me, it's easier because, like I said, we normally draw our x, y, z coordinate system with z pointing up.
Okay.
So then I can basically take this picture and just twist it a little bit to fit on the xz. Right?
So that's gonna be just shifted to the left too?
And also shifted
Oh yeah.
down to. You with me? So it's going to be parabolas, repeated parabolas, but what's happening to those parabolas as I step away from the xz axis? If I step with this direction, they actually go further down, right? See, maybe I should do this in green.
Follow the CY.
So they're forming like a tunnel?
Xz, yeah. So let's see, it would be like this here. And it has to be on the y equal 2. This is where isometric paper becomes very helpful. At y equal to 2, and then at z equal to -3. You with me?
Yeah.
So now it's a parabola here. So this, you can see what's going to happen in between y equals 0 and y equals 2. I'm going to have a parabola here that's a little bit down. I'm going to have a parabola here that's a little bit down. It's going to be like this shape. You with me?
Like an upside down mountain.
Yes, cool. And in fact, one of the ones we look at later, an example we give is walking on a mountain range. So that's because that's what it kind of looks like. Okay. Now that was sort of, I didn't purposely, I didn't even want to try to graph this, to tell you honestly, when I put it up here, because it is sort of a more difficult one to do for introduction to this idea. But you guys see how to start attacking these problems. That's the key point. If you're not sure how to put it all together in the end result, you can at least show me your traces and then what you tried to do in 3D. Right? Because I am being very honest with you that the 3D graphing is not going to be easy. That's why I try not to give too many of them.
So just go back to the point one more time. Same for y is equal to 2. It creates a shape that goes like this out from the xy plane. Is that
Because when I made y equals to 2, the shape is still going to be parabolic, right?
Yeah.
But now the formula is x squared minus 3. So as I move out on my y-axis, what happens to my parabolic shapes that go down? Right? So I've gotten a shoot, or a slide even, it's better. I think it shoots around, but the slide is better. Slide going down, right? So obviously if I made y equal to -1, it's going to be parabola y equal to -1, those negative ones cancel, so you get z equals x squared. So now it's going to be a parabola sitting right on the axis. So it's going like this, right? Okay. This would be a really good place for that minority report thing. Remember that old movie? Is that really old?
Yeah.
Tom Cruise.
There.
Is that at y equals -2?
Say again?
You have it at y equals -2.
I would do that.
It should be touching the vertex of the xy plane.
Oh, okay. It's being quick. Let's see. So if I make y equal to -1.
Yeah.
If I make it y equal to -1.
That's -2.
Is that -2?
Yeah.
Oh yeah, you're right. It has to be right there. Thank you, thank you. I already had a -1 there, is what you're saying. Okay. There it is. Cool. So it's going up and down. Right. That is why there are certain surfaces that are easier to graph, which is why we make you do those by hand. There are certain surfaces that are not as easy to follow what's going on, because these things are naturally going to go on top of each other. And after you've put them down, you forget, is that pointing this way or is that pointing that way, or what the hell? So isometric paper is going to make this a lot easier. Some of you guys do the little dotted lines to show you where your points come from. Not a bad idea because then your brain automatically puts it in the right perspective, right? Okay, cool. Let me see if this guy's. Let me show you a few pictures that are actually certainly better than mine.
You say I was gonna go end up being in a circle, like the steering wheel type, or are you just gonna go down?
In the y direction, it's going to be parabolic like this. Now, we didn't even talk about what's going to happen to this
Yeah.
parabola, because that parabola is in the xy plane. What if I let z equal to 1 or z equal to -1? What's going to happen to it?
Shouldn't you have intersections of the lines on X, Y, if you do the other planes, shouldn't the lines intersect?
How do you mean, sorry? If I do the,
So like if you do the XZ plane,
I never did
the
graph.
first one,
yeah,
What
the
you did?
xz,
it
this here.
should, those lines should intersect with the XY parabola. And when you extrude
Yes, exactly. That's what's going to happen.
each line should
Yeah.
intersect.
Cool. I like it. So let me show you these pictures. Maybe this will make it easier to see. So, for example, on this one, it's a little easier possibly to see this. But obviously, they intersect at this point, for example, right? So this parabola here and this green parabola there, they intersect at that point at the top. When you get more complicated functions like this, and I need to wait to throw this up here, it'll be a little easier for me to show you. When you look at it in one dimension, parallel to one coordinate plane, it could be doing something, but it could be doing something else at the same time in another direction. So here, this is really too basic to get the idea, but it's circles. If I look at it this way, if I look at it going this way, it's just circles getting smaller. But then what are all those circles connected to? Parabolas. And that parabola is what's defining how small they get. You with me? This line, and this is the point that I wanted to get to on here. This line here is equal to -y minus 1. There it is. You can see it at the bottoms of these parabolas. That parabola sits on that line, so if I move out a little bit, it's got to go down, so it sits on that line. It sits on that line all the way down. So what you're saying is, what you end up with, those surfaces, they have to agree with the other perspective, or else you get this disconnected surface. It can't possibly be true. So let me put it up here. It'll be a little easier for me to show you if I have something to point at. What did you go?
You have your computer on?
Yes. That's a good.
Might be a good time for a break.
There it is. Cool. Wait, what time is it? Oh yeah. I've been sort of talking for a while. Yeah, let's do that. Let's take a break. Come back at 1:35. It's a 10-minute break. I'll get this set up to show you what's going on.
I have more colors. That would
Oh,
help.
thank you. Yeah. I just always forget to stop by the print shop. Those are non-standard issue colors. I like that. Yeah.
Yes.
is nice because you can see. Obviously, I'll tell this to everybody when they come back. You can see the cross section in the XZ. I mean, in the XY direction. So, do you guys understand what I mean when I say that? If you cross it with any plane parallel to the XY plane, what shape do you get? And actually, I can show you. This is kind of nice.
Is it a circle or ellipse?
It's definitely an ellipse. Do you see that?
Ellipse, yeah.
Yeah. I wish they would give the. This is kind of stupid. They don't give the equation. Figure 1210 in the book. Who's got their book open? Figure 1210. I think it has an equation that goes with it. This one? 1210. Oh.
This one?
1210. Here we go. The equation.
Square plus 4y.
Oh, they don't have an equation. It's just an example. Shoot. Okay. So this, let me get it back to. I like it. All right, stop it, Jeff. You're making me dizzy. And the XZ plane, it's parabola, and the YZ plane is a parabola. So it's a lot like that ghost we did, just turned the other way. The ghost been put on his head. And in the XY, instead of a circle, it's now connected by ellipses. Right? So it's just an example of the flexibility you have with what the shape can be in all these different directions. Yeah.
Now, obviously, those are the simple examples. You're probably going to start giving us, different angles.
There's got to be. I mean, just like you start off in algebra, you start with a line, then a parabola. You eventually end up with logarithms, and you end up with exponential. Trig functions.
Yeah, so you have a deeper level of knowledge, understanding. So when you angle them, when you angle the planes so they're not parallel with the coordinate planes,
the equations get disgusting. So you have the same shape, but if I turn it just a bit, the equations get pretty disgusting.
It's a different.
And that's actually part of what linear algebra does, is it tells you how to more easily transform an equation based on a reorientation of the coordinate system.
So you're going to lose symmetry. You're going to have asymmetrical ellipses.
Well,
in the ellipse case,
the minute you turn it at an angle, it's asymmetric according to that coordinate system you've got set up.
Right. Yeah.
Yeah.
Can I ask you a question about the homework? Or the
Oh, this is cool. This is what I was trying to do. What's up?
Can I ask you a question about the test?
Yeah.
Wait. So how do you know which of these to choose? Because I basically chose it by picking the ones that added up to something close to 180.
Gotcha. The way you've got to do it is realizing from the beginning that basically your triangle's got, here's your U, here's your V, here's your W. So for any pair, they're pointing the wrong way. So if I want this angle, V should be pointing the other way. Right? They don't want to point at each other, so you don't want W pointing the other way. So you want to do negative V dot W.
Okay.
So that would just really just change that number there.
Okay.
So if you would have put into here, this came from where again? This came from.
This one is VW.
Oh, this is after subtracting from this, and this one came from this. And if you would have put, oh, you did the 180. Yeah. Now put a positive 62 in here, and of course you're going to end up with that one.
Okay.
Because this is basically saying you're back 62 on the x-axis, right? Because its cosine is x over hypotenuse. So if I instead want to go up 62 on the x-axis, of course I'm going to get this correct angle, which is how you got 180 minus this leaves you with the correct angle.
Okay.
So it's really, the whole thing boils down to whatever the dot product you got, change the sign before you do the inverse cosine, because you've got to turn one of them the other way.
Okay.
Cool. So it really goes down to
But
realizing.
This still doesn't add up to 180. So did I do something wrong?
Let me see. What were the angles you got? Yeah, those don't look familiar. Let me see.
So I got 86.86. I got.
Now that came from where? Here.
This
And
one
the dot
is
product
UV
was
angle.
3, so it should be negative 3. So that's where it started off.
And I took the complement of that.
But it should be the supplement. It's gotta be related to that 180, not to the 90.
Okay.
Cool, so, the actual answer should be, equally far away on the other side of 90, so it would be 94, or, 90, whatever, 93.14.
Okay.
And that's where maybe some of the missing degrees went to.
That
So
gives
you had
me-
if you would have taken this and did 180 minus this,
Mhm.
that would have gotten you to the right place for the angle here.
Okay, this. That was.
So here the 180 worked. Here it did, right? Because it's 180 you have to use, not 90. Yeah.
Okay.
Hey, what's up?
What time can I see you tomorrow?
Oh, let's say 11. Is that good?
Yeah.
Because then when you and I are done, I can just shoot over to, because the other meeting I have on Thursdays is flexible. So I can just tell her I'm going to come after my meeting with you. So 11 o'clock?
Yeah, that's
Okay.
cool.
Cool. It's your basic M&M.
Game bowl.
Can you put in your own?
Bull. What's that?
Can you put in your own equation?
No. That would be kick-ass cool. But it's beyond the capability of this. This is not Wolfram Alpha. The bad thing about Wolfram Alpha, I would love if they would mash them up, put this, but give it all of Wolfram Alpha's functionality, because then I could input my own equation and rotate the damn thing. But that would take a lot of computational ability. So this doesn't allow me to input my own things because it took all their computational ability just to make me rotate the ones they've got built in. Right? Oh yeah. Oh, and software packages you can do that because they've got it built in. These guys couldn't. I don't know why they couldn't. They probably could if they really, really wanted to.
Probably didn't want to spend the money on it.
No, this is a cool one. I like this. So you can tell, obviously. See the trace there? What is the trace? Good. So they call this a hyperboloid of one sheet versus, well, this is elliptic cone. Yeah, here we go. Hyperboloid of two sheets because they don't connect. I like that.
That's your thing right there, huh?
What's that? Oh. I've just been taping the whole experience.